there are many types of precipitation, but probably the most familiar to those of us in northern or southern California, especially the lower elevations, is rain. But if the raindrops get too small, they can actually become drizzle. We'll talk about that. The distinction between drizzle and rain is based on droplet size. But then there's frozen forms of precipitation, right? Rain, drizzle, those are forms of precipitation in which the water is liquid, non-frozen. What about frozen forms of precipitation? The most common and probably most familiar to people is snow. Okay, those flakes of ice that when deep enough can coat surfaces in what looks like a blanket. Okay, but there's other forms of frozen precipitation. There's sleet, small ice pieces that can either be clear or opaque. They make a tapping sound when striking the surface, like the ground. There's freezing rain, which is basically rain that freezes on contact with the ground. So the water remains as rain until it reaches the ground, then it freezes literally as it collides with the ground, and that can coat the surface in basically an ice cube. And this is a real issue for transportation. Okay, it can make it very hard to drive. We'll talk about how these different forms of frozen precipitation occur, right? Why sometimes does it snow, other times it might sleet, or you might get freezing rain. What's needed to get each of these types of frozen precipitation? We'll talk about it has to do with the vertical temperature structure of the atmosphere. And hail. Hailstones can become very large, and there are many hazards associated with hail, such as dents in cars, broken windows in houses and cars, damaged roofs. Okay, so let's start our discussion of precipitation types in detail. We'll first discuss non-frozen precipitation. Okay, now how would you define rain? Most people consider rain to be any falling drop of liquid water. But to the meteorologist, that falling drop of water must have a diameter equal to or greater than 0.5 millimeters, or 0.02 inches to be considered rain. So if falling liquid drops with diameters greater than 0.5 millimeters are considered rain, then what do you think about falling drops with diameters less than 0.5 millimeters? Well, those are drizzle. Okay, so when the liquid droplets are smaller, the falling drops have a diameter of less than 0.5 millimeters, they're called drizzle. Most drizzle falls from stratus clouds, okay, such as in San Francisco in the summertime. But small raindrops may fall through air that is unsaturated, partially evaporate and reach the ground as drizzle. Okay, so sometimes, especially if it's very dry near the ground, the air is very dry, sometimes the precipitation will be rain initially, and then the droplets start to evaporate on their edges and become smaller, and then the drops only reach the ground as rain. Okay. By the way, keep in mind that drizzle drops fall slower than raindrops. Okay. Occasionally, the rain falling from a cloud never reaches the ground because of low humidity that causes evaporation. As the drops become smaller, the rate of fall decreases, and they can appear to hang in the air as a rain streamer. These evaporating streaks or streams of precipitation are called virga. So virga is precipitation that enters a dry layer and evaporates before actually reaching the ground. Now, raindrops may also fall from a cloud and not reach the ground if they encounter rapidly rising air of an updraft, as is the case for thunderstorms. If the updraft weakens or suddenly changes direction and becomes a downdraft, those drops that initially were suspended or moving upward will fall to the ground as a sudden and sometimes heavy rain shower. Showers falling from cumulonimbus clouds are usually brief and sporadic as the cloud moves overhead and then drifts on by. So, for a rain shower, the drops are initially suspended by an updraft, but then they can fall when the updraft weakens or changes direction and becomes a downdraft. Even though liquid drops only need a diameter of 0.5 millimeters to be rain, okay, there can be some very large raindrops. The largest raindrops in the tropics have a diameter on the order of 6 millimeters. That's a quarter inch, okay? And you only need a few of these drops to completely wet your windshield, okay? But the raindrops only become so large before they will break apart or they won't be able to hold themselves together, okay? Now, what does rain look like? Question. What does rain look like? Or what do the raindrops themselves look like? We have a tear on number 1 is a tear-shaped raindrop. Number 2 is a spherical shaped raindrop like a ball. And number 3 looks like a hamburger bun-shaped raindrop. Which of these shapes is what a raindrop actually looks like? What do you think? Well, the answer is not number 1, despite common perception, but number 2 for smaller drops, number 3 for larger drop. So the tear-shaped drop has been depicted by artists for years, many years, decades even, but raindrops are not tear-shaped. Raindrops less than 2 millimeters in diameter are almost spherical and look like the number 2 raindrop here. The attraction among the molecules of liquid in surface tension tends to squeeze the drop into a shape that has the smallest surface area for its total volume, which is a sphere. But larger droplets with diameters greater than 2 millimeters take on a different shape as they fall. They look like the number 3 here. Slightly elongated, flattened on the bottom, rounded on the top. As the larger drop falls, the air pressure against the drop is greatest on the bottom and lowest on the sides. The pressure of the air on the bottom, that higher pressure on the bottom, flattens the drop, while the lower pressure on the sides allows it to expand a little bit horizontally. And this mushroom shape has been described as everything from a falling parachute to a loaf of bread or a hamburger bun. You can call it whatever you like, but remember, it's not tear-shaped. Okay. And by the way, what can rain do to the sky? It can improve visibility and make the sky look a lot nicer. Okay, so if it's been very polluted, hazy, a lot of aerosols has been in the atmosphere, a nice rain will really clear the air, improve visibility, make it easier to breathe. Okay, and a lot of rain will then, if it's been dry for a while, will turn the grass and from brown to green. Okay, but in California, there's a quote or a saying: "Brown is the new green." Okay, because of the drought we've had and the possibility of global warming leading to more drought in California in the future. Okay. Turns out that by 2100. The Sierra Nevada mountains will get anywhere from 30 to 90% less snowfall, and that's an issue because 60% of California's usable water comes from Sierra Nevada snowmelt. Now, here's a picture showing virga, the streaks of falling precipitation that evaporate before reaching the ground. Okay, and you can see these streamers, okay, of falling precipitation ending before they reach the ground. And this picture was taken around twilight hours, so you see the beautiful colors of the streamers, right? You see the yellows, the oranges, and reds of the falling precipitation that didn't make it to the ground. Now, let's talk about frozen precipitation. Let's talk about snow. In fact, most precipitation in middle and high latitudes begins as snow. Okay? Even in the summertime, much of the precipitation in the mid-latitudes, and basically all of it in the higher latitudes, begins as snow. Okay? In the summertime, it will melt into rain because of freezing level being higher in the summer above the ground. But in the wintertime, when it's colder in the mid-latitudes, or even in the late fall and early spring, it can reach the ground as snow. Okay. So it turns out for the high latitudes and the mid-latitudes, the Bergeron ice crystal process is very important for precipitation. That's how a lot of the precipitation begins. And then the falling ice crystals become bigger and snowflakes due to aggregation, but then they melt. Okay. And when does snow melt? Okay, as if the snowflake encounters air of a temperature of above 32 Fahrenheit, does it melt immediately? Not necessarily. Okay, not necessarily. Snow can fall at temperatures slightly above freezing. Okay, 34 to 37 degrees Fahrenheit. Okay, generally, snowflakes fall about 1,000 feet below the freezing level before completely melting. So if the freezing level is 1,000 feet above the ground, okay, and maybe the ground is a few degrees warmer, right? Remember, on average in the troposphere, the environmental lapse rate is 3.6 degrees Fahrenheit per 1,000 feet. So say it's 32 Fahrenheit at 1,000 feet, it's about 36 Fahrenheit at the ground. Those snowflakes could still reach the ground, okay, because it takes time for them to melt. And there's different states of the atmosphere that allow snowflakes to fall at higher temperatures. Okay, so if the air is very dry, then there's more evaporation, and evaporative cooling can allow snow to fall at temperatures well above freezing. Okay, so what can happen is the air is very dry, the snowflakes falling into warmer air above freezing. And because of the dry air, there's a lot of evaporation. So what happens is the edges of the snowflake melt into liquid, and then that liquid rain, the partially melted edges, quickly evaporates. Okay? And then that chills the snowflake. Remember, evaporation is a cooling process. And the melted edges have now evaporated, so the snowflake is back to being just frozen because the melted part evaporated and it's cooled down. Okay, so I've seen snowflakes fall at temperatures of 38, 39 degrees Fahrenheit. Either personally, wet snow at those temperatures, or also I've seen observations showing that. And I've even seen some observations of snowflakes falling at 40, 41, 42 Fahrenheit in very dry air. Also, strong downdrafts can allow snow to fall at higher temperatures. If there's a really strong downdraft in a cumulonimbus cloud, then the snow might fall so fast that it doesn't have time to melt before reaching the ground. Okay? Now, what do snowflakes look like? Well, they look like a lot of shapes, but they tend to be pretty symmetrical. Okay? This is a figure from the book showing a computer color-enhanced image of dendrite snowflakes. Okay? And there's that saying, no two snowflakes have the same shape. Okay? Now, we associate snow with cold weather, rightfully so, because generally temperatures have to be about at, maybe a little above or below freezing to snow. But what if it gets too cold? Can it ever be too cold to snow? Although many believe that expression, the fact remains that it is never entirely too cold to snow. Yes, more water vapor will condense from warm saturated air than from cold saturated air. Okay? But no matter how cold the air becomes, it always contains some water vapor that could produce snow. So even though colder air, quote, unquote, holds less water vapor at saturation, right? The colder the air is, then the less water vapor it has at saturation. We talk about saturation because generally when precipitation is falling, the air is saturated or close to saturated, right? It is at least in the cloud. And so as the air becomes colder, it can't hold as much water vapor. But even at very cold temperatures, the air is capable of holding some water vapor that could produce snow. Now, snowflakes tend to get smaller with lower temperatures because of the air at colder temperatures holding less moisture, okay? But Snow has been observed at temperatures as low as minus 53 degrees Fahrenheit, or minus 47 degrees Celsius. Okay, and in this case, the snowflakes are very tiny ice crystals. Okay, we usually associate extremely cold air with no snow because the coldest winter nights, tend to occur during atmospheric conditions that normally prevail with strong, high-pressure areas, sinking air that have few of any clouds. Okay, recall that, right? For strong radiational cooling, a very cold night, what are some of the conditions needed? Right, clear skies, so that the radiational cooling will be more effective. Earth's heat will escape to space. Right, you can't have snow with clear skies. Okay, but nonetheless, generally, the colder it is, the less capable snowfall. Okay, and so basically, much of northern Alaska is a desert. It's a polar desert. Okay, so they get a little snow, but not much because it's so cold. It's dry. Snow has interesting optical properties, especially compared to rain. This is a figure from the book showing how snow scatters. Remember, scattering is reflection in all directions. Snow scatters sunlight more effectively than rain. Okay, and here you are. Okay, looking at the horizon, and here's a cumulus congestus cloud, maybe cumulonimbus cloud. Turns out cumulus congestus clouds can produce snowflakes. Well, they generally can't produce rain, but the snow might melt into rain. Okay, when you look toward the sun, the region of falling precipitation above the melting level looks darker than below it. Okay, so the melting level can be seen when the sun is near the horizon. And what's happening is the snow is scattering sunlight more effectively, and so in the vicinity of it, so there's less light to reach your eyes, as opposed to the rain, where not as much is scattered in the vicinity, so more of it's able to reach your eyes. Okay. So when you see a change in color of the falling precipitation below a cloud, that's a signal of the melting level. Okay. Now, how does annual average snowfall vary across the United States? Okay, let's look at a map to see. Okay, we would like to know, which states get the most snowfall. Okay, and how much, right? So here's a map showing average annual snowfall in inches, okay? By colors. Yellow here, no snow. Mild, moderate green represents 0 to 3 inches of snow on average per year. Remember, these are just averages for annual snowfall. Okay, one year could be snowier, one year could be less snowy. Okay. Dark green represents about 3 to 6 inches of snowfall. This turquoise green represents 6 to 12 inches of average annual snowfall, so half a foot to a foot. Okay. Blue, 1 to 2 feet. Okay, of snowfall per year on average. Dark blue, 2 to 3 feet. Purple, 3 to 4 feet. Gray, 4 to 6 feet. White, more than 6 feet of snow per year. Okay, so if you look at the map of the U.S., and this map shows the continental U.S. and Alaska, right? Which state's missing? Hawaii. Because Hawaii really doesn't get snowfall except for very small areas of the mountains on the Big Island, okay? What do you see? What are some patterns you see on this map, okay? Well, average annual snowfall totals tend to be low in the southern states, okay? Especially, you can see here at the lower latitudes, these states closer to the tropics along the Gulf Coast, and higher as you move north, okay? Florida basically gets no snow per year. Snowfall is extremely rare in Florida, okay? Especially in southern or central Florida, okay? It can get cold here, but it's rare to get snow, okay? So snowfall can happen occasionally, every few years or so in parts of the Panhandle, but it's still rare, okay? It's rare to get snow along the Louisiana coastline, although once in a while, New Orleans will get snowfall. Okay, snowfall is also rare along the Texas coast. Okay, but if you get further away from the Gulf of Mexico, okay, into the more northern parts of these Gulf Coast states, like northern Mississippi, northern Alabama, northern Georgia, okay, you might get a few inches of snow per year, okay? Maybe you get 1, 2, 3 days a year with a dusting of snow, okay? Texas is interesting because while Texas is almost unprecedented in places like Houston, northern Texas, the extreme northern part of Texas, close to the Oklahoma border, can actually pick up 1 to 2 feet of snow a year. Okay, there are mountains here, so the higher elevation definitely plays a role. And speaking of elevation, right, why do you think the pattern of yearly mean snowfall in the western third of the country is so complicated? It's all the topography, right? There's the Rocky Mountains that extend through Colorado, Wyoming, into Utah, okay? There's the Sierra Nevada Mountains you see here, right, playing a role in snowfall in Northern California. Cascade Mountains in Oregon and Washington, Coast Ranges in Oregon and Washington. And in the eastern part of the U.S., you even see the effect of the Appalachians. Okay? So, some of the snowiest states in the U.S. are what? Maine, basically the entire state with the exception of the coastline, gets 4 to 6 feet of snow a year. Okay, partly because that state is so far north, right? Notice how far north it is, okay? And New Hampshire and Vermont, okay, get a lot of snowfall, as does upstate New York, okay? As do some of the Great Lakes states, okay? Much of Colorado is mountains, okay, especially the western half, and they get a lot of snowfall there. Okay, and there's peaks, right? The 14ers, lots of 14+ thousand feet mountains in Colorado. Okay, Utah, you see, okay, snowfall, and yeah, even the Sierra Nevada can get several feet of snow per year. Okay, again, and as you notice, as you begin to move, even in this part of the U.S., the south and into the Midwest, it's pretty flat. Okay. But you definitely notice as you go to higher latitudes, your average annual snowfall increases, right? By the time you get to Chicago, you're dealing with 2-3 feet of snow a year. Okay, and it's very cold in the wintertime in Chicago, so much of the snow will stay there for long periods of time without melting. What about California? Looking more in detail where we live. You do see the coast ranges picking up snowfall, especially farther north. You do notice actually not the entire Central Valley is dormant from snow. The northern end of the valley actually can get a few inches a year. So for example, Redding, California, which is at the northern end of the Sacramento Valley, about elevation 500 feet, because of its, well, for one, it's slightly higher elevation, but more so because of its farther higher latitude. Much of Alaska does not get large amounts of snowfall per year because it's so dry. Okay, so basically for the northern 2/3, maybe 3/4 of Alaska, you're only talking about 3 to 12 inches per year for the most part. Okay, maybe higher in some pockets. Okay. Now, what about other forms of non-frozen precipitation? Let's talk about how they form. What about sleet? In order for sleet to occur, there needs to be a strong temperature inversion present. Okay. Sleet is a transparent ice pellet. Sleet pellets generally bounce when striking the ground and produce a tapping sound when hitting a window or piece of metal. Sleet occurs when snowflakes enter a layer of above freezing air and melt. However, the then melted raindrops enter a deep sub-freezing layer, a deep layer of air below freezing, near the ground, and refreeze into small ice pellets before hitting the ground. Here's the vertical temperature profile for sleet. You have a nimbostratus cloud, which can produce snowflakes. The snowflake melts as it enters a layer of air above 0 degrees Celsius, 32 degrees Fahrenheit. Melts into a raindrop. Then near the ground, there's a deep layer of air below freezing, and so the raindrop refreezes into a sleet pellet. Generally, you need a layer of sub-freezing air on the order of probably at least about 1,000 feet. But the deeper, the more time for the raindrop to refreeze into sleet. And here is a picture of sleet on what looks like a porch. Notice these small, pretty clear pellets of ice. And you see the difference between snow in the sense that when snow falls, the snowflakes combine and they produce a pretty uniform looking surface, like a blanket. But for sleet, you can see the individual ice pellets. Whereas for snow, you can't see the individual ice crystals on the ground when they come together, although you can see the individual snowflakes in the air, right? How about freezing rain? Well, its formation is similar to that of sleet, but a little different. So it has a similar vertical temperature profile as for sleet, but the sub-freezing layer near the ground is shallow. So for sleet, the sub-freezing layer near the ground has to be deep, on the order of probably 1,000 feet or more. But for freezing rain, it's very shallow. And so then what happens is the rain does not refreeze into an ice pellet or ice pellets before reaching the ground. It only freezes on contact with the ground. And storms with substantial amounts of freezing rain are called ice storms. Okay, so when you hear it's icing or there's ice falling, well, that's freezing rain. Freezing rain can create a very beautiful picture as it coats surfaces in an ice cube, but it can create a lot of traffic mayhem as roads become skating rinks for vehicles. And it can create a lot of power outages because the ice gets very heavy. It can weigh down the power lines and break them. It can also weigh down trees. There's a comparison of the temperature profiles for sleet and freezing rain. Notice for sleet, there's a deep freezing layer near the ground, so the raindrop has time to refreeze into an ice pellet before reaching the ground. But for freezing rain, the freezing layer near the ground is so shallow that only when the raindrop strikes the ground does it refreeze, and it freezes on contact with the ground as opposed to before reaching the ground. Here is freezing rain coating tree branches, and this ice can get extremely heavy. There was an ice storm in 1998 that extended from New England to Canada. It left millions of residents without power. It caused over $1 billion in damage. This ice storm occurred in January of 1998, and here you see, basically these are these large, very large electric transmission towers and power lines, and you see one of the towers coming down because of all the weight of ice on it. And I used to live in Portland, Oregon, and they've had their share of ice storms. This is actually a picture from the famous ice storm in 1996 in Portland. And here's a sign for a freeway, and you see the freeway sign showing Portland Marine Drive and the entrance to West Interstate 84, US Highway 30. The do not enter sign, you see them coated in ice, okay? And also what can hang from signs and windows are these icicles. Icicles. Very hard to drive on ice. It's often worse than driving on snow. Now, freezing rain, as well as freezing drizzle, are somewhat rare, across much of the U.S., although more common in some spots. Here's the average annual number of days with either freezing rain or freezing drizzle over the United States. California, most of California, most of Arizona generally don't have to worry about this, except the extreme northern fringe of our state, extreme eastern fringe of Arizona. But in a city like Portland, or a city like Seattle, right, the Rose City, the Emerald City, you're going to generally have a few days a year with freezing rain or freezing drizzle. Okay. Even over parts of Louisiana, Mississippi, Texas, it happens. But it's very common for this to occur over the northern Midwest, Minnesota, Iowa, the Great Lakes region, okay, Michigan, Wisconsin, and extreme New England, Maine. There are some pockets with up to more than 2-3 dozen days a year where freezing rain or freezing drizzle occurs. Speaking of ice, aircraft icing can be extremely dangerous. Ice that forms on aircraft, it's a real hazard because it changes the aerodynamic flow of the wing. Makes it hard to fly. It can also damage rear-mounted engines. Here's a picture showing ice buildup on the wing of a small aircraft. So this photo is taken from inside the plane, and the person taking the photo is looking out the window, and you see ice covering the wing. Okay, that would be a pretty scary sight, I think, for me at least. Not sure about you. And so, because icing is very dangerous, there have been accidents due to aircraft icing. Typically, planes undergo de-icing during inclement weather. So, this plane is having its wings sprayed with an antifreeze before takeoff during cold, inclement weather. It helps keep the wings and the other parts of the plane warm enough to prevent ice from forming, which again can change the aerodynamic flow of the plane and damage the engines. Right, you don't want the engines to freeze. Now, speaking of ice, there's not only sleet and freezing rain forms of ice, and even snowflakes are made of ice crystals that combine, but there's another form of frozen precipitation involving ice that we need to discuss, and it's very exciting. It's hail. Hail stones are pieces of ice that fall from thunderstorms, either transparent or partially opaque. They have great size ranges. They can range in size from very small peas to golf balls or even larger. Hail is produced in a cumulonimbus cloud, so generally hail only falls from cumulonimbus or thunderstorm clouds. And hail forms when frozen raindrops or other particles are carried by strong updrafts inside a thunderstorm. Hailstones grow via accretion. Here's a figure illustrating how hail forms. Raindrops are being sucked into an updraft. Okay, the updraft has very strong vertical upward motion. So the raindrops get pulled in. Then they rise above the freezing level and freeze. And they form these particles of ice, and the hail can grow in circulating convection currents. Eventually the hail gets too large for the cloud to hold it. Its downward velocity exceeds that of the updraft, and so it falls to the earth. And as it continues to fall in a downdraft, it grows larger, but sometimes before leaving the base of the cloud, if the updraft is strong enough, it gets sucked back into the updraft. It can grow larger and larger. Okay, the faster the updraft speed, the larger the hailstone can grow. How big does hail get? Well, here's pictures showing some money, right? Some loose change, a dime, a penny, a nickel, a quarter. And you see these hailstones the size of less than, smaller than, or about the size of a golf ball, right? Imagine getting hit by that. But it can grow even bigger. Baseball or softball sized hail. Hail is most common over the eastern fringe or plains just east of the Rocky Mountains. This is the number of days per year on average with hail for the continental U.S. And what you see is that it's actually very rare in northern New England. Despite the fact that Maine gets a lot of snowfall and a lot of freezing rain, it doesn't get much hail. Generally, they don't get the strong enough thunderstorms for it to occur. And hail is pretty rare in Florida, even though it's interesting. Florida is actually the state with the greatest number of thunderstorm days per year. Yet, it's also a state with very little hail because even though they get thunderstorms there, it's so warm that the hailstones melt before reaching the ground. In the Bay Area, generally a few days a year will produce hail, mainly in the winter time or early spring. You see that. In the Bay Area, 3 to 4 days per year on average with hail. Rarer in Southern California. Although in November 2003, a rare hailstorm dumped more than 5 inches of hail over a part of Los Angeles, causing gutters to clog and floods to occur. Occasionally, if hail is heavy enough, it can actually appear as snow and accumulate a few inches. And so what you see here is that parts of northeast Colorado, southeast Wyoming can get 6, 7, 8, 9 days a year with hail. And hail is also common in parts of northeastern Arizona and northern New Mexico. And here's what a hailstone looks like. You see the different layers showing how the hailstone went through a cloud of varying water content and temperature. The largest recorded hailstone by circumference in the U.S. is shown here. It was about the size of a soccer ball. It had a diameter of about 7 inches and therefore a circumference of over 20 inches. And there's a YouTube video that you can watch. Hail destroys windshield. It's very entertaining. Let's watch it.
Big hail. I have to stop. Wow. Oh shit. Oh shit. Oh, here's the windshield. Fuck. Ah, damn it. God dang it. Ah. Oh shit. God dang it. Thank you, sir. May I have another? Thank you, sir. May I have another? Thank you, sir. May I have another? That just came inside of my car and broke. Here's my windshield here.
So, even though that storm chaser's windshield got destroyed, he still kept his calm. I liked his sense of humor, right? Thank you, sir. May I have another? So, in some parts of the U.S., there's insurance that will cover windshield damage from hail. Now, question. How is precipitation measured? What scales are used? Let's talk about that. Typically, precipitation is measured in inches, either inches of rain or inches of snow. Assuming no runoff into rivers and lakes and oceans or evaporation, if an inch of rain fell, the ground would be covered by a pond of water 1 inch thick. Now, an inch of rain and snow are different. Frozen precipitation takes up more space than liquid precipitation. So, on average, for every 10 inches of snow that would be equivalent to 1 inch of liquid water. This is just an average. It varies depending on temperature. At temperatures just above freezing, the surfaces of snowflakes will partially melt as they fall. That produces a wet layer surrounding the snowflake, allowing for other snowflakes to attach, generating a larger snowflake. So typically, the largest snowflakes, big fat snowflakes, occur at temperatures just above freezing. Whereas lower temperatures have smaller snowflakes, and that affects the ratio. But generally, if 10 inches of snow fell, then if it melted, it would produce 1 inch of rain. Okay. Now, what is used to measure rainfall? Well, a rain gauge is an instrument that collects and measures rainfall. The standard rain gauge has a funnel-shaped collector attached to a long measuring tube. And it permits very precise measurements to the nearest 0.01 inches or 1/100th of an inch. The cross-sectional area of the collector is 10 times that of the tube. So rain falling onto the collector is amplified tenfold in the tube, which permits measurements of very great precision to as low as 1/100th of an inch. If less than 1/100th of an inch falls, that's called a trace, and that's not considered measurable rainfall. Here is a standard rain gauge. So you see the funnel, okay, the collector, and here's a scale. And typically, the rain gauge would have diameter on the order of 20 centimeters, about 8 inches, 7, 8 inches, and a height of 50 centimeters. About 1.5 feet. It varies depending on the individual rain gauge. But you can buy a rain gauge online for literally a matter of a few dollars. There's another rain gauge called the tipping bucket rain gauge that does not actually hold the water, but removes it every single time 0.01 inch has entered. So the tipping bucket rain gauge has a receiving funnel connected to 2 small metal collectors or buckets. The bucket beneath the funnel collects rainfall. When it accumulates to 0.01 inches, the weight of the water causes it to tip and empty itself. The second bucket immediately moves under the funnel to catch the water. When it fills, it also tips and empties itself, and the original bucket moves back beneath the funnel. Each time the bucket tips, an electronic contact is made, causing a pen to register a mark on a remote recording chart, such as on the computer, laptop here. Adding up the total number of marks gives rainfall for a certain time period. One issue with the tipping bucket rain gauge is that during each tip, it loses some rainfall and therefore undermeasures rainfall amounts, especially during very heavy downpours, okay, where you might get several hundredths of an inch falling at once, and it tips, and as it tips to record the 0.01 inches, some of that rainfall actually gets lost. The tipping bucket rain gauge is the standard rain gauge used in automated weather stations, such as those at airports across the U.S. Now, rainfall intensity, not amount, but intensity, how heavy it is, can be measured remotely using radar. And radar is a form of remote sensing. Remote sensing devices can measure precipitation from distances away from where it's occurring. Pulses, electronic pulses, are sent out by radar, which then reflects or bounces off the raindrops. So radar, basically, which stands for radio detection and ranging, a radar will send out electronic pulses of energy, and the pulses of energy will reflect off raindrops come back to the receiver where the energy pulses were sent out. But the heavier the rain, then the more scattering and more energy sent back. Basically, there's a connection between how heavy the rain is falling, intensity, and the type and amount of radiation sent back, energy sent back. And there are many stationary radar dishes around the U.S., but there's even radar on wheels. Okay, so it's even possible to bring a radar dish onto a large truck. And this can be useful during storm chasing, for storm chasers who want to have really close radar images. Here's how radar works. Again, Doppler radar tower. So there's a radar dish covered. Typically, the radar dish is actually covered at these official stationary radar sites to prevent dirt and bird poop getting on it. And so the echo, the pulse is sent out, raindrops return energy back to the radar. Okay. There are official National Weather Service office radars. There's the one on Mount Umunhum in the Santa Cruz Mountains at an elevation of near 3,000 feet. There's one in the southern Sacramento, northern San Joaquin Valley, near Walnut Grove, California. Okay. But there's also TV radar dishes. For example, Channel 5 has their own radar on Mount Vaca in the near American Canyon, and Channel 7 recently got their own radar dish on one of the mountains in the Marin County. And that's useful because it turns out, we'll talk about it more in a bit, radar beams can actually sometimes overshoot the raindrops. Okay, and we'll talk about that. Now, there's also computer algorithms and programs designed to detect different types of precipitation. See, snow in blue will scatter energy back differently from mixture in pink, rain and snow falling together, and rain in shades of green and yellow. So actually, not only can the radar image show how hard the precipitation is falling, right? You see the varying colors. The darker the color for pink mix or blue snow, the heavier. And then rain, as you get darker green into the yellows and reds, you're getting heavier and heavier precipitation. But also, the actual type of precipitation can be colored. Okay, so you'll know, oh, is it snowing or is it raining, right? Or, you know, how far do I have to go to get from rain to snow? Now, the Earth is curved. The Earth is not flat. Okay, maybe you agree with that, maybe you don't. But the radar dish sends out energy, and owing to the fact that the Earth is curved, and the fact that the radar beam is sent out at an angle, the farther away from the radar dish you are, the higher the beam height. Okay, so you see it's sent out at an angle. It's not at flat. It's generally sent out at an angle upward. And then as you go farther and farther away, the Earth is curved, so it's getting higher in the sky. See that? So closer to the beam, here, the radar would detect this rainfall. But here, farther away over the city, it might be raining, and the radar could overshoot the rain, go over the tops of the clouds. And so on the radar image, it would show no colors. It would look dry when it's actually raining. This is a major issue for the North Bay precipitation because of the fact that the National Weather Service Bay Area Office radar is on Mount Umunhum in the Santa Cruz Mountains. It's very far away from the North Bay. And so sometimes the radar image will show no rainfall falling in parts of the North Bay when it might be moderate to heavy rainfall occurring. And so what's done is sometimes the National Weather Service forecasters, as well as amateur and weather meteorologists and weather hobbyists, the news meteorologists, will look at the Channel 5 radar. KPIX has their own radar dish on Mount Vaca, which is just east of the North Bay, and so it's much closer to Marin County, Sonoma County, and so it can help fill in the gaps of rainfall or coverage that the Mount Umunhum radar overshoots. And Channel 7 recently, just a few years ago, very recently, also got their own radar dish, actually on a North Bay mountain. Okay, so that's helpful. Here is the site of the National Weather Service Bay Area radar. If you ever looked southwest of San Jose, and you see that peak, and you see what looks like a box, well, to the left of that box, to basically the south of that box, is the radar dish. If you look very closely, you see a covering on the radar dish. And so actually, if you live or go to South San Jose, especially southwest San Jose, you'll be able to see it better. Okay, that's it for Lecture 6.